So, we are discussing about convolutional neural network, and in this lecture I will provide some examples of CNN architectures or convolutional neural networks which are used for different particularly for image and object classification. So, the first the very first network which was introduced for as a in the applications of image classifications, in fact in document image processing, document image processing or character recognition, this is called LeNet, and it is a gradient based learning applied to document recognition, as you can see. And this architecture uses two convolutional layers. There are two pooling layers, two fully connected layers, and it was reported in 1998. It was quite long back, and it is quite a pioneering work in that sense. And its number of parameters, it was around 60,000, and number of floating point operations per inference was 341k. That means about 341,000, and it uses sigmoid as a nonlinearity function. So, this is a diagram which shows schematically how this architecture looks like. So, you can see that there are convolution layers, and then you have the subsampling, which means it has the pooling layers, and as you have discussed, there are two convolution layers, two pooling layers, and there are two FC layers, and finally you get the output out of this process. Then in 2012, in fact, this network is used, and this has provided very good result for the ImageNet classification, and this is called AlexNet. So, in this network, it uses a normalization of the responses, that local response normalization, and its architecture it consists of 5 convolutional layers, and you can it has also 3 pooling layers, and you can see that the first 2 pooling layers are adjacent to their convolution layers, but the last pooling layers it operates after processing through, after getting the process data through 3rd, 4th and 5th convolution layers. That is what it is designed, that is how it is designed, and there are normalization operations after first and second convolutional pooling layers, and there are 3 fully connected layers from which the output is and then finally there is an output layer. So, the number of weights in this case was 61 million, and number of floating point operations is 724 million. So, it is a very large network compared to very primitive network of LeNet earlier what has been reported. And here they have used ReLU as the nonlinearity, that is one of the major change of nonlinear functions in neural network. So, a schematic diagram of AlexNet has been shown here. It also shows some of the information related to the size of the input. Say it processes 224 by 224 inputs. It takes filter sizes of say 11 cross 11, and then it uses max pooling of 5 cross 5. Finally, you can see that the feature representation what you are getting 4096 is the dimension of the feature representation, and that is finally classified for the 1000 nodes. So, this is how this classifier is used. So, if I would like to count the parameters of AlexNet, let us consider how the parameters could be counted. Say consider the input image size of 227 cross 227 cross 3 images. That is the input size. It was not 224. It is 227 cross 227 cross 3. And the first layer, convolution layer, there are 96 filters, each of size 11 cross 11, and it is applied with a stride 4. So, the gap between two samples in the input pixels, so that stride should be 4. There should be 3 it should leave 3 samples, and at the 4th sample it should operate with the convolution operation. So, what should be the output volume size? So, as we know that it is related with the dimension of input width and height and also the filter size. So, along length and breadth you can see that it has to be the 227 minus 11 is the filter size and divided by 4. So, that is how the dimension, and then you add with 1. So, because of the central you can add with 1. So, this is the this is the expression we have discussed earlier also. So, the 55 would be the size of the length and size of the breadth, and your depth is the number of filters, that is 96. So, the size should be 55 cross 55 cross 96. So, that should be the output volume, it is 55 cross 55 cross 96. Similarly, what should be the number of parameters in this layer? So, the number of parameters involves the filter weights and also biases. So, since there are 11 cross 11 filters, that is the size 11 cross 11 cross 3, that is the filter size. So, number of parameters will be 11 cross 11 cross 3 for one filter, and since there are 96 filters, it should be 96 into 11 into 11 into 3. That is the total number of parameters, that is without bias. And if I consider each should have a bias, so for each filter there would be one bias. So, you have to add another 96 biases. So, it should be 90 this number, which is around 35K, around 35K or 35,000, that is the approximate number, and that should be again plus 96. Then consider the second layer, that is pool 1. It has 3 cross 3 filters, and which is applied at stride 2. So, what should be the output volume size in this case? So, once again 55 minus filter size 3 divided by the stride 2 and plus 1. So, output the length and breadth should be 27. So, output volume would be 27 cross 96, because the depth the input depth of the input was 96, it remains the same, and that is what is your output volume. And what is the number of parameters in this layer? And as we mentioned that in pooling layer there is no parameter involved, you do not require any weight or bias. So, number of parameters would be 0. So, in this way you can count parameters by knowing the size of the filters, and you can count you can also determine the size of the output by knowing the size of the filter and size of the input and number of filters, that is also important. Other network that is also quite distinct, that is ZF network. It is I am basically providing you some kind of historical evolution of CNNs. So, ZF network came from Alex network, the changes, these modifications. So, what it does, it uses filters of smaller size. So, earlier it was 11 cross 11 stride and stride 4. In ZF network they use 7 cross 7 stride 2, and but what they do also, they have used more number of filters. Say for example, in conf 3, 4, 5 in AlexNet you have 384, 384 and 256 filters. In ZFnet you have 512, 1024 and 512, and it has improved the accuracy of the image classification for the ImageNet dataset. So, this is one, that smaller the filter size, it is smaller in filter size is smaller, and but more filters in layer is used. A schematic diagram is shown here. It shows the size of the different processed output and also the size of filters and other things. Next evolution of this CNN architecture, next stage was VGG, and here in this architecture you have a very you have a good number of deep layers. So, the idea is that you should have smaller filters, smaller even than the ZFnet, and you should increase the number of layers. So, in ZFnet you have smaller filters, more number of filters. It is not only more number of filters, also increase the more number of layers, and by doing that they could increase the performance of the image classification using the same data set what I was referring. So, in this case VGGNet it uses different kinds of number of layers in architecture. There are 13 layers which is called VGG 13. There are 16 layers which is 16 or 19 layers which is called VGG 19. And only 3x3 convolutional filters are used with stride 1, pad 1 and 2x2 max pool with stride 2. So, the filter specification is very simple for VGG network. So, here the observation is that deeper the layer, better was the accuracy. In this particular VGG network, suppose it is, I am not sure which number it is. In a typical VGG network, it is 138 million number of weights and number of floating point operations for each inferencing, it is about 15.5 billion floating point operations. So, one example of VGG network, it has been shown here. You can see that typical sizes of input which starts from 224 cross 224 cross 3 and then it downsamples till 7 cross 7 and finally, the feature representation goes towards the 1 cross 1 cross 4096 and then you use the softmax probabilities, you use the output layer 1000 plus classification. It has been observed in or it has been found in the VGG network that stack of 3 cross 3 convolution layers has the same effective field as one 7 cross 7 convolution layer. So, successively if you use 3 cross 3 convolution layer, let me explain that. So, you have an image. So, apply 3 cross 3 convolution with this image, then you produce another image, then you apply against 3 cross 3 convolution. In this way, successively you do it, the effect would be that same as if you have 7 cross 7 convolution at a single stage. And so this is one advantage. So, that is why you have so many number of layers, but you are having the same effect and you have more nonlinearities introduced and that would give you the fewer parameters also, because if you are using this stack of 3, then you get fewer parameters. Like for this case, you have say 3 into 3 square C squared, that many number of parameters should be there if you assume C channels per layer, C is a constant. Whereas for 7 cross 7 filter, it is 7 square C square. So, that number is large compared to 3 into 3 square, which is 27. Then we came across GoogleNet, and in GoogleNet you have more number of layers, 21 depth and total 57. It introduces inception modules, that is the novelty in GoogleNet, modifications. So, what it does, instead of using a filter of same size in a particular layer, it concatenates output of filters of different sizes, and that increases the power of the model. So, it has only one fully connected layer and its weight is number of weight is 7 million and number of floating point operation is 1.43 billion. And the architecture, example architecture, there are 9 inception modules as I mentioned. So, there are 3 convolution layers and there are 2 pooling layers followed by these convolution layers. But after that you can see it is inception layers, again there are pooling of inception layers. So, if I explain, if I give an example. So, GoogleNet also provides a very good performance, 6.7% top 5 error. So, this is one short diagram, short picture of Google Net, how does it look, and you see that these layers are inception layers. So, these layers are inception layers. So, it is using different sizes of filters and then it concatenates this filter. There is a enlarged diagram here. So, here it is shown that from the input there are filters of 1 cross 1. So, 1 cross 1 means it is filtering along the depth only. So, your filter weights are along depth only. Then there are 3 cross 3 convolution filters, 5 cross 5 filters and 3 cross 3 pooling, and number of filters with different sizes also they vary, say 128 1 cross 1 filters, 192 3 cross 3 filters, 96 5 cross 5 filters, and then of course 3 cross 3 pooling, which does not require any number of filters, which should give you the same depth value of the input. So, finally, you can say that if I use 128 1 cross 1 filters, and your output would be 28 cross 28 cross 128, that would be your output. Similarly, for 3 cross 3 convolution, and here by performing zero padding, you are keeping the input size same, output size same as the input size. So, that is also done in the inception module. So, you have 28 cross 28 cross 192 output from this module. So, this is giving 28 cross 128, because there are 128 filters. This will give 28 cross 192. This will be giving 28 cross 96, because there is a zero padding. So, you are keeping input and output same size, and this will give 3 cross 3 pool, but there is no stride. So, this will also give 28 cross 256. So, total input size, output size would be say 28 cross 28 cross, and there are so many channels. So, this is how the inception module works. It increases the number of channels, and sometimes it reduces the number of channels, like here instead of 256 the number of channel becomes 128 here. So, that was the modifications done in Google Net, and it has found to be giving good performance. Then the next kind of deeper model is the residual network or ResNet, because the problem, if we increase the more number of layers, it has been observed that it causes overfitting and it is harder to optimize, because the gradients they get vanished. So, since for the vanishing gradients you cannot run the optimization, it dies soon as we go deeper. So, this ResNet will discuss the architecture. So, this is the problem. So, you can have a good training error, but your test error would be quite high if you increase the number of iterations, if you go by more number of layers. So, this is a normal CNN. It is a CNN with less number of layers, and this is a CNN with more number of layers. So, you will have this problem that your error will be higher. So, in the residual network or ResNet, what we try to learn the residual errors. So, it fits the residual mapping instead of directly fitting the fitting the data itself. So, as you can see in this unit, that what you are learning the residual part fx, because there is a skip connection here, it is called skip, and it is added with this residual part, and then only you are getting the output hx. So, what you are learning fx is hx minus x, which is the residual part, that is what you are learning. So, this is one schematic diagram where ResNets are shown. As you can see that the skip connections are there regularly, and your number of layers could be very large. It could be more than 100 now, and it has increased the performance of the classification to a great extent. There are other examples of networks also, like some list is provided here. I am not going to read all of them. So, you may go through these references. In particular, let me point out one network which is called mobile net. It is used for low end applications, and here all the filters are of size of 1 cross 1. They are all separable convolutions. So, there are few things we would like to discuss about training of this network. First thing is that we would like to preprocess the training data set. Different kinds of preprocessing is required. We need to normalize the data with respect to the variances of the data that we have to normalize. Then decorrelation is also required, which means diagonalization of the covariance matrix. We know the decorrelation of data is principal component analysis that we have learned, and whitening of data is identity covariance matrix. So, which means that during normalizations you have to divide it by the variances, you have to normalize the ranges, and or you can subtract the mean. So, different kinds of preprocessing operations that may involve while using this data for the purpose of computation. Then you may require to generalize your data set, because the data set what you have with labeled data set, that may not capture the all variances of in the class. So, that is called data augmentation, because by doing some simulation you can also generate some more data. So, like you can perform different kinds of geometric operations on data images, say horizontal flips, random crops on scaled input, color jitters, you can add noise, you can add variances, add different kinds of color variations, distortions, then transformations. So, there are different kind of simulations you can do on the given input data set and generate more input data set and use it for training. Then you need to initialize weight. There are different policies for initialization of weights. I will discuss that, and train the network by updating the weight parameters. So, there are few training tips that is required that I would like to provide here. So, you should start with small regularization and find learning rate that makes the loss go down. So, regularization parameter. So, there is a loss function, you have the regularization term and also the loss function due to the cross entropy term, for example. So, it is a linear combination. So, start with the regularization component, keeping it as small, and also try to find out learning rate that makes loss go down. So, you can overfit very small portion of the training data and then train first few epochs with few samples to initiate the hyperparameters. So, first you have to introspect how it is behaving and try to select those parameters which are giving you which is providing you the directions of convergence, good directions of convergence. So, those parameters you need to consider, and because it is very time consuming. So, once you fix the parameters, then again empirically you have to observe how it is behaving. So, these are certain tips. By using it you can reduce your time of experimentations. So, if you find there is a big gap between training accuracy and validation accuracy, then it is a overfitting case. So, what you should do, you should increase the regularization term in that case, or if there is no gap, then you may increase the model capacity. So, one of the policy for initialization of the weights is called transfer learning, and in this case even if you have a small data set, you can work with deep learning paradigm. You do not require a lot of data set to train CNN. Usually deep learning requires a lot of data set, because what you can do, you can use a pre-trained network which has been trained using a very large data set for some applications, but use that feature representation in your own application. So, pre-trained models can be initialized for CNNs at the early stage of training. So, the example here I will be providing, say for example, you train on ImageNet data set a particular network. Here we have shown that there are few convolution networks and then fully connected networks given the image, and it also shows number of channels, etc. And now in your small data set you fix this portion. So, this is your feature representation. So, the whole feature representation is fixed. So, you can freeze this and you can transfer the weight which has been learned in this network, you can transfer it directly to this, because your architecture is kept same. So, that is the constraint, you have to keep the same architecture. So, you transfer those weights and use these weights to learn the features, and then only you train the output layer, that means the final classifier, you only train that part, and you can reinitialize and train for the classification in your particular to your problems what you are working on. If you have a large data set, bigger data set, then you can have some other, you can have other kind of policies. For example, in this case, you can consider all the fully connected layers to be trained, and by keeping your feature representations only at this point. So, you can consider that, and your lower learned, you have a you can fine tune finally. So, what you can do also, that you can fine tune once you get a convergence some weights, then you can again fine tune. So, you can train with your input data samples and using a lower learning rate, and which is like 1/10 of the original learning rate. I mean, that is a good starting point, and then you can vary it. So, these are different pragmatic policies, and some of the intuitions, heuristics, those are used while training a good deep neural network, which takes a lot of time and also a lot of resources. And finally, a good network, when it gives you a result, that requires a lot of experimentations. It involves a lot of experimentations. You should understand that. So, with this, let me stop here, and we will continue this discussion on deep neural architecture in my next lectures. Thank you very much for your listening.